Okay. All right. So we are at lecture 6. I'm going to continue talking about sensor security. Specifically, I'm going to talk about faults, and then we're going to move a layer up and start talking about malware. Okay. So if you remember last time, we said that things start getting wrong once we start the interaction with the physical world, right? And if it didn't have any sort of interaction, we probably would have been fine. Although once I start talking about side channels, you would see that actually that's not the case all the time. But majority of the time, the interaction is really what caused the problem, okay? And then this interaction could have been prevented and could have been fixed if we didn't have bugs or wrong assumptions or just some unknown assumptions. But in reality, this is not, feasible to achieve. And that's why we are, having this problem. We talked about sensors as kind of like the first way of getting into a system and kind of attacking a system. We said that essentially there are 3 steps or 3 domains that an adversary might be interested to attack the system: the physical domain, the analog domain, and the digital domain. Last lecture was mainly about the physical domain and how the environment could be changed in order to attack a system. Today, I want to talk about the analog and the digital domain, and then move further away onto the digital space, okay? And then talk about, the majority of attacks that probably you have heard before and you know about them. So we're going to talk a little bit more about those type of things, okay? We said that generally the attack scenarios are 4 different things. There's transduction attacks, which we extensively talked about. But other than, transduction, which usually tries to kind of inject some errors at some point, and then that error propagates all the way through, we want to also have things like denial of service attacks and integrity or fault attacks, and finally digital attacks. So I'm going to talk about these 3 in this lecture. Okay. We also talked about how we can model a sensor, and we essentially say that a model is nothing but series of transfer functions, and this transfer functions has some inputs and has some noise. And in order to be robust against the transfer function and noise, you want to have the final outcome that is robust. That is, doesn't change if you change the noise or change the inputs. And we finally said that the attacker also tries to kind of modulate this noise, change this noise, right? And that was really what we're going to get in an attack scenario. Okay. We gave you 3 examples. One was about drones and how by sending some acoustic signal at a frequency which caused the kind of resonance frequency of the gyroscope, we can crash a drone. We talked about how we can change the dosage of a medicine by changing the lights, right? And then we also finally talked about how we can inject inaudible commands to a voice command system, right? And most of them were kind of working on the physics aspects of the sensor. One was working on this fact that there is resonance frequency. The other one was based on this fact that there is saturation modes in sensors, and the third one was based on this fact that there's non-linearity in sensors. And if you have enough understanding of the physics of it, then you can actually launch an attack on these systems. We also talked about defense. We said that generally we are interested in 2 kinds of defenses: prevention and detection. We gave you examples on each one, so go back and take a look at those to review that. Okay. So now let's talk about a new concept, and that is faults. So if you go back to this figure, essentially transaction attacks kind of covers those aspects of the system, that you change things in the physical domain, that's transducing to some wrong signals, and that propagates all the way through. But what if we don't want to change the environment? What if the environment's actually sending the correct data? And here at the amplification or filtering or digital conversion or even processing, we want to create some changes. Okay. And we generally define that as false because the original value that's supposed to be read was, let's say, X. And by default, we are kind of like flipping some or all of these bits to some X prime. And this X prime will be propagated all the way through. And very similar story that we said so far, that is could result in some information leakage, it could result in some availability issues, or it could result in some form of actuation that we don't want to, some actions that we don't want to, right? So basically I want to talk about this part now. And let's talk about different types of faults. Okay, so there are usually, like, we will call it 4 different types of faults that we are interested. And generally the different types, it depends on which level you're applying your fault. Okay, at the instruction level, you want to change some operands or some instructions. Remember, what you would do is, in most cases, you have some form of a core, right? You have some CPU or core, that what it takes is a program, right? And this program is going to execute, list of instructions, and then it's going to give you an output. So what you want to do in terms of faults is, actually, if I somehow manage to change things in this program, the output would be different, right? So this change in the program could be change in the instruction itself. So for example, let's say you were supposed to do add X1 and X2, let's say, and then to write the results to X3. Okay. So what I can do is that essentially this add is nothing but a list of, zeros and ones. If you remember back in the day when you were talking about, computer architecture and the way ISA works, you probably have heard things like opcode, right? And the way that we kind of like, understand which instruction is which is this opcode. So what the attacker can do is that if they can flip bits, they can, for example, flip add to, let's say, subtract, or you can flip add to a multiply. So essentially, by changing the control bits, they can change the operation, right? So that's one thing that they can do. The second thing that they can do is changing the values, all right? So these are just registers, right? So what they can do is that if they cause bit flips, if they cause faults in their system, for example, let's say this was equal to 1 and this was equal to 0. If they can like flip this, maybe this becomes like 4, or this becomes -3 or something like that. I'm just making up numbers. So what they do is now they're changing the values, right? And changing the values can also result in some form of different behavior, right? So that's one thing they can do at the instruction level. Essentially, once everything has been sensed and converted and all those things, now we go to the processor and now we are kind of start flipping things. Okay, so that's one thing we can do. The second thing we can do is that even further than that, we can change things at the microarchitectural level. Okay, and cause some wrong operations there. A more common one is at the circle level. Okay, so if a little bit lower than the other two, that you change the operation, mechanisms or operation environments of the device. For example, you change the voltage, you change the frequency, you change the temperature, you change all these things, and what would result in is that the device does not operate properly. I'm going to give you an example for this one later on in this lecture, so you can actually see what do I exactly mean by that. And finally, you can similarly that you change the environment in order to kind of send a wrong message. Maybe you can also change the environment to cause a fault. Okay, so again, like examples are injecting some electromagnetic signal, increasing the temperature, changing the interface, things like that you can do in order to attack the system. Okay. And then the interesting thing about faults is that faults not necessarily physical. So as opposed to transduction attacks that was purely physical, faults could be either physical or it could be digital. I'm going to give you an example for a physical, fault attack. I'm going to give you an example for a digital fault attack. Okay. If you want, there are seats here if you want to come. Oh, you're charging? Okay. There is a charger here as well if you want to. If you go all the way, in the first row. Your choice. So let me give you 4 different things. I'm going to talk about physical fault attacks. Then I'm going to talk about an example of a digital fault attacks called DVFS attacks, which change the dynamic voltage and frequency scaling. I'm going to then talk about Brawlhammer as a very specific type of faults that we can apply to the systems. And then finally, I'm going to talk about jamming and contamination and then compare it with spoofing. Okay, and these are kind of examples of false attacks that we are interested in. So what is the goal of the fault attacks? The goal is similar to the previous cases, is causing some malfunction to achieve either information leakage. So you can actually create faults to leak some information. I'm going to actually show you an example for this. But in most cases, what you really want from the fault as an adversary is impacting the integrity or the availability of your system. Okay, so these are the most common ways of using faults in systems. So an important assumption about the hardware when we are talking about faults is that we always assume that the underlying hardware, the embedded hardware, is running the software correctly. As in, when we're talking about faults, we don't assume that hardware can randomly run things differently. We always assume that the hardware has been implemented correctly, has been running things correctly. So if that's not the case, that's not a fault per se. What it is just a fault in the design. It's a wrong design. Okay, so we always assume that hardware can be trusted and hardware is operating correctly. If it doesn't, then it's just a problem of the design. It's not an attack, or it's not a fault attack. Okay. Later on, at the end of kind of this class, we're going to talk about hardware Trojans, which is kind of breaking this assumption about the hardware, that no longer hardware actually does what it's supposed to do. Okay, but based on this assumption, what hardware faults does is temporarily cause the hardware to malfunction. Okay, so so what really hardware faults or faults in general do is breaking this assumption about the hardware always doing the same thing, and for some transient time, for a short period of time, causing the hardware to do malfunction. Okay, so that's what's really happening with fault attacks. Usually there's this sort of flow for faults. There's kind of like 5 different steps. So obviously the first step is creating the fault, but then designing and creating the faults. Then we usually apply the fault at different levels. Okay, we might actually apply the fault at the physical layer. This could be a timing fault, this could be a power fault, this could be an EM, a heating, a light, various different things. Then you inject this into the system, and then it has to manifest itself, right? So you inject, for example, you change the power, and that should cause a bit flip. Okay, we call that a fault manifestation, right? That something changed either in your logic gates or in your memory cells, in your sequential bits. Some bits has to change, okay? And that's when the manifestation happens, okay? Then it has to propagate, okay? So for example, if you have various different steps or very different layers in your hardware, let's say you have memory, you have register file, you have status registers, you have data paths, you have controller. If something flips, for example, 0 becomes a 1 or 1 becomes 0, that bit flip has to propagate all the way through such that it becomes something important. If, for example, you flip a bit, but it doesn't propagate to the place that you want to, that doesn't matter, right? That's not a successful attack in terms of a fault attack, okay? So it has to propagate usually from the ISA level, the microarchitecture, to actual application layer, right? To actual output of your system. And then you should be able to observe that fault, okay? So for example, you're having some form of a program like this that you want to verify something like an S and say, okay, if S is equal to something that we know before, we can trust it. If it's not, then we don't trust it. And what the attacker can do is basically either flipping this S or maybe flipping this R. So the final observation, exploitation of your fault is the fact that, for example, something that wasn't supposed to be verified or authenticated, now it's authenticated or verified. Okay. So what is happening is really at the very low level, you're changing things in physical domain or digital domain. And that's change all the way goes through layers of hardware and microarchitecture and software to eventually create something meaningful that the adversary wants to achieve. For example, in this particular, figure that I'm showing you here, what's really happening is that your authentication is failing. So, for example, remember all those things that we discussed last week about, digital signatures or MACs. Let's, for example, say this is the verify function for a MAC. And then you're generating just a wrong tag, right? As an adversary, you're generating a wrong tag. And what you would expect is that this function is working correctly. So it checks your tag and sees not correct tag. So this R should be, for example, equal to 0. Okay. So what the adversary does is that in addition to generating this wrong tag, they launch a fault attack that start flipping bits such that eventually this R becomes 1, which means that now the software can trust this tag, and that's basically mess up the entire thing. Okay, that's really what is happening with fault attacks and what you really want to achieve in a fault attack. Okay. So let's talk about different types. Similar to transduction, there are different ways and modalities. So for example, you can use things like glitches, you can use overclocking, you can use electromagnetics and lasers, you can use pulse, you can use various different things. What is really important here is that you are at the analog/digital domain, so it's slightly different the way that you want to impact the system. It's a little bit different than what you would do on sensing side. For example, on sensing, you would send some acoustic signal and that would result to be translated and transduced to some values. Here, no longer that applies. So you want to change things other ways. So if you want to overclock your system, you want to change the voltage, things like that. An important thing about faults is the intensity of the fault. Okay, kind of similar to what we discussed for transduction attacks, but here intensity is more important. As in, for example, if you change the temperature and changing the temperature will cause faults, how much temperature are you changing? How much extra energy are you injecting into the system for that fault to happen? Right. So if you have to inject 1,000 degrees of Fahrenheit in order to the system to break down, that probably is not a very sophisticated attacks to use, right? Another important things about timing is about faults is the timing, because since we want to kind of create this attacks and inject it all the way through, for example, for this particular example, I need to inject the fault exactly at the moment that this S is being compared, right? So for example, if this function starts at time t1 and ends at time t2, your fault should happen somewhere between t1 and t2, right? If your fault happens afterwards, then there is no point because already R has been checked and test has been failed. So the timing and the exact timing of the faults is really, really tricky. And that's what makes fault attacks really hard to pull off in real examples. Okay. Another thing that you need to also pay attention to is the notion of what we call white box versus black box versus gray box, which means that how much do I know about my system? For example, for sensors, all you need to know is basically what sort of sensors this device is using. You don't need to know the back-end processing and the steps that it takes all the way to the software. For faults, you probably need more information. You need to know when it's happening, how it's being processed, and all those things. So white box means that you have full knowledge of the entire end-to-end system, and black box means that you have no information whatsoever about the system. So like how much information you need to have in order to, launch of successful attacks is important here. And finally, is this a remote attack or is this a physical attack? Remote attacks is mainly falls into digital domain attacks that I'm going to talk about, but physical ones are attacks that you change something. For example, you change the temperature of the environment and that cause a fault to the system. Okay. Any questions so far? Any questions about the things that we discussed last time? Okay. So let me give you a more concrete example, and this is a fault that you can do in order to do information leakage. Okay. Remember we talked about AES, right? We talked about AES and we told you that, for example, AES can have 10 rounds, right? So what people have found was during the final round, so if you actually let's say the output of the 9th round is V, and this V goes into the 10th round, which is, if you remember, there was some going through mix the sub bytes and mix row, which we usually call it the S box, and then XORing it with the key to get the final value. So if you remember those steps, if you are at the final round of that, what you can do is, if I somehow can flip bits or flip bytes into that input of the final round, what I can do is that I can see the difference between V and V prime, right? And then I can also see the difference between C and C prime, right? And what I can do with this is, then I can maybe kind of do some search in order to find this K. At least I can, reduce the search space based on seeing V and V prime and C prime. Remember, for something like AES, we assume that we know the input and we know the output, but we didn't know the internals of this crypto system. What faults can give you is that if you somehow manage to change things here, then you can run this one time with V and get C. So you see V and C. Now you will have this ability to change bits or bytes as your will. So you can, for example, change 1 byte and create V prime. And then you can also see C prime, because that's the output of the AES. And combining this two, people have shown that some clever searching algorithms can reveal at least some part of your key. Okay. So how do we actually do this? How do we actually flip this bits? There are various different ways that you can do it. For example, people have shown that if you inject a really strong laser to the system, if you have like a laser very close to the device, you might be able to flip bits. If you change the temperature, some other people have shown that you can flip bits. How we actually flip bits is a separate technological story. But the fact that if you were, if you had that opportunity and that capability to flip bits at your will at the last round of AES, then you can actually break the assumption about the key and find the key more efficiently. Okay. Any other question? Does that make sense? Yeah, you have a question.
So does this method still work if we end up flipping, like we flip the right bit that we wanted, but we also flip like other bits as well?
So the main thing here is that you should know what your V prime is. Okay. So it doesn't matter that you are flipping which bits. All you need to know essentially is you should know exactly what your V prime is. V prime is what happens after you're flipping bits. So for example, if your method is flipping 3 bits, if you know which 3 bits they are, then you should be good. Okay. And then what you can do is maybe you can repeat this until you find the right, overlap between bits, and then continue this. So that's kind of like the idea. But essentially, people have shown that you can do it even with single bits. Any other questions? All right, so this is kind of an example of what we say an information leakage scenario for faults, because at the end of the day, what is happening here is that you're not, changing the integrity or availability of the system. What you're really trying to do is finding what this K is, which is the secret part of the system. So it's pretty serious attack. although it's pretty strong attack, in order to flip single bits, this is not an easy thing to do, especially for very complex integrated system. In many cases, this is not a realistic or effective method. So it's not like, oh, you can flip any bit you want anytime you want. Under some very, special circumstances, you might be able to actually launch an attack like this. And there are examples of this. If you're interested, you just take a look. If you just search this, you will see examples of real demonstration of this attack. Okay. So before actually jumping into another examples, as you can see here, an important things that you need to pay attention to is what we call the manifestation and propagation, right? For this particular case, the manifestation and propagation was quite simple because you change this, you see this, and then you can measure it, right? But if you, for example, flip this bit and then your C doesn't change, or there are some other complexity that you won't be able to observe what C or C prime is, then this attack wouldn't be successful, right? So the propagation and the manifestation is an important part of any fault attacks, because if you flip something, you should be able to observe something. If you cannot observe that, then it doesn't matter what you can flip, right? At the best, what you can do is some form of a denial of service. But in most cases, what you really want to do is being able to see what you're changing, okay? And then another thing that I want to mention is there are also regular faults that can happen. There are regular bit flips that might happen just because the temperature might just suddenly change. There might be some alpha particles that might, target your system. Your system might work on extreme conditions, for example, your space shuttle or your device that's, a minor device that goes under the sea. So these kind of things can happen as well. And we usually call them regular faults, okay? So fault tolerant systems are actually quite popular and very established area of research in many domains of electrical engineering. What we're talking about here is fault attacks particularly. And the difference between the two is false attacks are intentional, as in the adversary can actually think about this and plan for this and pick the right time for this in order to launch the attack, versus fault attacks are mainly just some random processes, right? Something randomly happens. And then the other biggest difference between attacks and regular faults is the intensity, okay? So usually the fault attacks much more intense than the regular faults that might happen in your system, okay? So two things. One is the planning and pre-planning for the adversary, and the second thing is the intensity of the attacker is really what makes as a regular system versus an adversarial system is the difference between the two. So something that is robust against regular faults is not necessarily robust against malicious and attackers, okay? So just keep that in mind. So let me give you two examples of other types of attacks. I already gave you one. Let me give you two more. The first one is what's called corkscrew. And what this does is kind of like, some form of what we call a digital fault attacks that change the voltage and frequency of the system in order to kind of change the operation of the crypto systems that we have in the underlying system. It's been published in Usenix 5-6 years ago. So what it does is in order to understand how this works is it's based on this energy management systems that we usually use in our systems called dynamic voltage and frequency scaling. So what it does is essentially, have some sort of software. It looks into the operation of the software, the voltage versus frequency. And what it's going to do is that it's going to induce some faults in order to eventually find the key in the system. Okay, so how do they do it? In order to understand it, you have to first know what DVFS is. So DVFS is generally this concept that we don't need to always use the same voltage and same frequency for our devices. What we can do is that we can dynamically change voltage and frequency depending on the workload. Why should we do that? The reason for doing it is just to save energy. Okay. Usually, the energy is some function of voltage, usually with linearly, and also a function of frequency. Okay. And what you want to do is if you reduce the voltage, you can reduce the energy. If you reduce the frequency, you can reduce the energy. So you want ideally to be as low as possible frequency and as low as possible voltage in order to preserve as much as energy that you want. But on the other hand, lower voltage and lower frequency means lower performance, right? So you want to have, devices that can clock really fast, right? You can switch really fast, and you want to have voltage so that you can pump more current, so that your delays goes down. So on the other kind of like in the opposite direction, for performance, you want higher power, higher voltage, and higher frequency. Okay. So what we do, we make a dynamic system that usually like sits between the hardware and software. We call that dynamic voltage and frequency scaling, or DVFS. And what it does is kind of like, having some form of, what we call power governor, or some form of, controller logic that's looking to the workload, looking for the requests from different, part of the system, including both software and hardware. And then it's going to change the voltage, voltage regulator and frequency regulator of the system. And this is really, really fast. So we are talking about, milliseconds, nanoseconds, depending on what sort of system you're using. So depending on like, if your system is off, then your voltage and frequency will be down. The moment for example, I open my phone and start unlocking it and start using it, the voltage and frequency are going to jump up. Okay. And then you're gonna start using it. All right. Same thing, for example, for refresh rate of your screen. It's usually you bring down the refresh rate to save energy. The moment you start using your screen, the refresh rate goes up, because refresh is also the same thing. Higher refresh rate means better performance, but it means more energy and more power. Okay. So that's the story of DVFS. A little bit more formal. Your power is a function of voltage, frequency, and the capacitance. It's CV square F. So actually, if you reduce your voltage by half, your power will go by a factor to the power of 2, right? So it goes by 1/4. Frequency, although it's linear, so if you do a frequency by half, your power goes by half. Okay. But as I said, you want to have this dynamically so that, if your voltage goes up, your performance goes up. If your voltage goes down, your performance goes down. Performance and performance. On the other hand, if your voltage goes up, your power goes up, and so on and so forth. Okay. So what we usually do is that we don't have kind of like random, voltages and random frequencies. What we have is operating point pairs. Okay. In most of these devices, there's usually pairs, as in if you change the voltage, for example, if you reduce the voltage by 1.5 or whatever number that you're reducing, your frequency should somehow follow the same. So you never make your voltage divided by 2, but keep the frequency as is. So you typically just have some form of range of points, okay? And each device has its own recommended operating points, okay? So for example, say that, your voltage can, for example, stays the same, and your frequency can go up until, for example, 1.6, 1.7. Then at that point, if you really want to, increase your frequency even further, then you really need to also increase your voltage, okay? And then finally, if you want to, for example, hit 2.7, which is the maximum for this, for example, particular device, which the authors were looking at, you have to, for example, have the voltage somewhere at 1.1, something like that. Okay. And then if you really want to go really, really down, then, for example, your voltage can go up all the way close to 0.7, and your frequency is going really, really low in order of hundreds of megahertz. Okay. So that's kind of the idea of DVFS. What could happen is if you actually kind of like, don't follow this and start changing things, there's some voice coming from somewhere. Okay. So if you don't do this, then there is kind of like a line which, if you kind of exceed this line, you're going to reach into what we call an unstable mode. All right. In unstable mode, you no longer know what's going to happen to your hardware. Your switching no longer works correctly. Your system doesn't work correctly, and so on and so forth. And for example, for the same device, they found, for example, that this is kind of like the line that if they kind of cross this line, the system becomes unstable. All right. So what do they do? And then, so this is not, same for all the devices. So for one device, for example, this stable unstable line is something like this. For another device, this is more smooth. Okay, so it's not necessarily the same thing for each device. So what they can do is they can play with this, configuration, and they found that they can actually kind of like, shift the operating points to somewhere here. For example, your device was supposed to have this voltage and this frequency, but what the trick that they show is they can, for example, force the system to have a higher voltage or a higher frequency, like having this point here. Okay. And if they do that, then the device becomes unstable. What does it mean by unstable? So if you kind of like go back to your old, undergrad courses about designing flip-flops and digital logic, you probably remember that we had this thing called setup time and hold time for our flip-flops. So usually if you're designing your logic, you typically have, two components. You have a sequential component, which has some notion of memory, right? It's, holds values over and over again. And then you have also a combination part, which is just a logic. There's no memory involved in it. And in order to design your system, you typically have a sequential, then a combinational, and a sequential. Okay, so your combinational logic is sandwiched between your sequential parts. We typically call this like in a pipeline design, so that at every clock cycle, you just kind of move into the next one and next one and next one and next one. The reason for doing this, then you can actually clock your system much faster, and then you can kind of like, divide the combinational part of your program or your circuit from each other, right? So what you will do is you have a combinational part, then you have a register or flip-flop, then you have another combinational part, then you have a sequential logic, then you have another one. And what this gives you is that here you can like, work on one set of inputs, here you can work on the other set of inputs, here you can work on another set of inputs. So you isolated these combinational parts from each other. And then by each clock cycle, this data goes into here, this one goes into here, and so on and so forth. Okay. But in order for this to work, if you go back again to your digital or circuit logic design courses, the time it takes for this value to be kind of stored in this flip-flop, what we call is that the setup time. It's usually these flip-flops are what we call edge triggered, which means that once the positive edge of the clock comes, whatever data that is here is going to be, stored here. Okay. And usually it's this time, we need to do that. What we usually do is, if I draw the clock here for you, and then if this is my combinational logic, what you really want to do is your combinational logic should be kind of ready at this point. Okay. There should be some time before the positive edge of the clock that your data should be stable. If the data changed during this period, then we call that, data is unstable, which means that there is no guarantee that this data, let's say if it's 1, is going to be actually properly stored in your flip. Okay, we usually call this a setup time, which means the time it takes for the flip-flop to be set. All right, so if it's really, you are really pushing and you're making really close to the trigger of your clock, then your flip-flop might miss it. Okay, that's kind of like a very high-level idea of this. So you want to have a little bit of buffer before your positive edge comes. Okay, And another thing that you want to have is that you don't also want to quickly change your combinational logic right after the trigger. You want to also hold it a little bit, then let it go. Okay. So usually for each flip-flop, you have what we call a setup time and you have a hold time. And this setup time and hold time depends on the technology, depends on the design, and so on and so forth. They're usually really, really small compared to the clock cycle, but you really need to make sure that these setup times and hold times are correct and always less than the maximum that are allowed. Okay, so that's kind of the idea of how your system works. So how does the fault occurs? The fault occurs if you actually violate either the setup time or the hold time of your system. Okay, so if I actually clock faster than what I'm supposed to, or if this delay is actually longer than what it's supposed to, then I'm gonna either, violate my setup time or the hold time or both of them together. So what will happen then? What will happen then is that you're thinking that you're storing 0 here, but you're really storing 1. So there could be random behavior, your bit flips, and all those things that can happen. Okay. So based on this, that's basically what they did. So they said that, okay, I know that there are some, known pairs of voltage and frequency that are supposed to follow. What I can do is that I can change the firmware of the device such that I can violate this pairs. Okay, so instead of operating in one of these, black points, I'm actually, operating somewhere close to these blue points. All right. What does it do? It's going to actually violate the way that we design the circuit. So it's actually going to violate either the setup time or the hold time of my device. Why? Because if you change the frequency, if you make the clock frequency faster, then your hold time or setup times will be violated. If you reduce the voltage, also your setup times might be violated because your delay actually shoots up, right? Lower voltage, higher delay. Okay, so either of these two or combination of these two will result on something like this. That, for example, you run a piece of software, you expect that this will be your output, but what you can do is that by, very intelligently pick the points that you want, you can actually change any of these bits or bytes as you wish. Okay, and that's exactly what these guys did. So what they did with this was two things. They showed that they can actually infer secrets of AES using this trick. Don't worry about the trust zone part for now. What is happening is that, remember I told you that if you have the last round and you create the faults, you can actually read the key. Similar idea here. So basically, instead of if I go way back, I show you this example, right? I told you if I have this capability, I can find the key. So this is kind of very relevant to how they launch their attacks. So they change the voltage and frequency at right time. They create these pairs. They look at these, different ciphertexts, and they manage to extract the key correctly. And the next thing about their attack was this is purely software. So they can actually change things in the firmware and at the software level. They can create this faults at the software level. They can actually analyze the results at the software level. So it's very quick, very automated, and very fast in terms of how well this attacks can work in a real system. Okay. Another thing that they did is that they also launched an integrity attack. Remember that example that I told you that, for example, you want to verify a function, right? And you want to, for example, verify that the MAC is actually correctly computed. If you can actually flip bits, you can also flip control bits, right? So, for example, you say that this device is trusted or not trusted. I can also find a way to flip that particular bits as well. But they actually showed that this is also possible. So what they did is they created this concept called self-signed applications. Think about this as some applications are not allowed to be executed on your device if they're not coming from a trusted source, okay, a trusted designer. So what you can do is that with this trick, you can basically run any arbitrary app on the device, which means that, the adversary can basically, download their malware, run it on the system without actually somebody being able to detect them or stop them or and to do any sort of defense against them. Okay. So pretty strong attack. They also talk about some defenses. I'm going to actually revisit the defense for faults once I finish with the second example as well. But for example, they show that what you can do is limit the operation of these points. Maybe if you don't allow the user to change those points, you can fix the system. Maybe you can create cross boundaries. Maybe you can have some operating points for some part of your circuit and some for the others. Maybe you can create better regulators, create redundancies. Maybe at the software level, you can create some randomization and so on and so forth. I'm not going to talk about the details of this. I will revisit this later on when I'm talking about the defenses. But definitely, if you're interested, go and read this paper. Okay, it's a really nice paper. It discussed the details of the attack and the defenses. Question?
The problem is, how do they know exactly when the process is running is using the critical data?
Yeah, so that's a good question. The question is when do we know that, for example, you're actually using AES, right?
Only do you know the time? Can you after that can you affect the circuit or?
Yeah. So what is happening? There are some assumptions involved here, but typically what they do is, oops, somebody's calling me. So if you actually know when AES starts, then you know exactly when, for example, your 9th round starts, because this is a very deterministic algorithm. Okay, so that part is not that difficult to kind of figure out. As long as you know when it starts, then you know when the particular place that you want to attack the system happens.
It's also very hard to know when exactly the transaction is going to execute to start to launch the AES.
Yes. So the second question now is, how do I know this starts, right? And there are tricks that you can use. For example, you can trigger AES. For example, whenever I send a message to this device, they have to decrypt it, right? So what I would do is that I intentionally send a message, wait for the AES to happen. You can also look at the other indicators. For example, you can look at the power consumption. And then if the AES starts, probably there is a jump or surge in the power consumption. So you can actually align this in order to find where it actually starts. So there are various different things you can do. Another thing that you can do is that nothing prevents you to call AES yourself. Okay, as a user, you don't have access to the key, but you have access to the APIs. Okay, so you can actually call AES as you wish. And what you can do is that during your attack, you can, whenever you're ready, you're going to call AES, and now you know where exactly it's going to start, and then you're going to launch the attack afterwards. Does that make sense? But probably if you read the paper, you'll see more details. Yeah.
How did it say the frequency of the malware development?
So there is actually these are available at the user level. That's the main reason. So usually you can actually, if some of you play with Linux, you can actually change your voltage and frequency. You can change the mode of your system, for example, from performance to low power to dynamic. You can actually set the frequency. For example, Raspberry Pi, you can actually tell them exactly which frequency and which voltage you can play. There are performance reasons for it. So whenever they were designing it, they were not thinking about a possible attack like this, but it was mostly for cases that as a developer, you want to, for example, be able to dynamically change things, right? And that's a very valid kind of request. So that's why they made it available to developers, but now it's kind of come back and bite us, right? So that's the problem. Any other questions? Okay, let's pause here and then come back and talk about row hammers after this, okay? Maybe 2-3 minutes. All right, let's continue. So the second example that I want to talk about is about row hammers attack. Row hammer is actually, first was introduced in 2014, but it's been since then it's actually been very, very popular and interesting attacks. There is recently also there has been more interest in using row hammer attacks. The slides I'm going to show you is actually borrowed from the original presentation of Rowhammer. So what is a Rowhammer attack? It's attacks on the modern DRAM systems, okay? And the idea of Rowhammer is this, that, DRAM is usually kind of designed into this 2D arrays. There are rows and there are columns. And typically when we are accessing DRAM, we're accessing row by row, okay? So we read one row together and then go to the next row and next row and next row, okay? And when you're reading, you typically just read one row, okay? If you want to access the next row, you have to issue another memory read, okay? So what they found was this very interesting observation that if somebody tries to kind of access one particular row over and over and over, what will happen is that some random bits at the adjacent rows are going to flip, okay? Very, very, weird behavior, but it's by keep reading a particular row, what will happen is that there will be some other bits in different rows that has nothing to do with this row. They're just physically adjacent to that row, and they're gonna flip. All right, so the bit's gonna be flipped from 0 to 1 or 1 to 0, and that's a huge problem because essentially what the adversary can do is just keep reading different lines in the memory and then just completely messing up the entire memory as they wish. And as I said, originally they showed this observation, but it gets actually more sophisticated and show that you can actually select which bits you want to flip and do all those things. So you can actually be very controlled attack. So you can actually go to that, if you know where the sensitive data is stored, you can find an adjacent row and access that and flip that particular row. And this is particularly interesting because we typically in modern systems, we have this notion of isolation, okay? When I'm talking more about microarchitectural side channels, I'm going to talk more about this. But to give you a quick overview, when we have isolation, it means that if I have like two processes, process 1 and process 2, in memory, I'm going to basically divide the memory into regions, okay? I'm going to say, okay, this region belongs to, for example, P1, and this region is going to belong to P2. And if P1 tries to read anything from this part of the memory, the operating system is going to block this, okay? And this is very important and very basic requirements in any secure system, that you have to have memory isolation, as in a sense that if one process tries to access some other process data, it should not be possible. We usually achieve this using address translation and so on and so forth, which I'm not going to get to. But usually we're going to really, logically divide the memory into regions and say that, okay, this region belongs to you and this region belongs to me. I cannot access your data. You cannot access my data. Everybody is happy, right? So the basics of multi-tenancy. But with this, what is happening is that even though P1 is not accessing P2, they're supposedly just accessing their own. But if these two lines manage to sit next to each other on DRAM, which is actually possible, then by just accessing my own lines, I'm actually flipping bits in this different one, okay? And that's really concerning in terms of security, okay? So that's the idea of the DRAM. Let me go a little bit more closer to the parts and to the details of it. So as I said, typically DRAM is organized into banks, and within banks we have rows, and within rows we have cells. Okay, so for example, one row is a combination of many cells, usually like 64 bytes. Even bigger, 4 kilobytes, depending on like how many rows you want to store. And then the way it works for DRAM is that DRAM, at circuit level is really just a CMOS, a MOS transistor, and a capacitor. Okay, and this MOS transistor is connected to what we call a bit line and a word line. Okay, the word line selects the transistor, and the bit line is really let's kind of connect the switch. So what is happening is generally reading from DRAM is a leaky process. Okay, why? Because this capacitor is kind of like full. So let's say, for example, this capacitor is something like this. It's actually like, you know, a glass that is full. What is happening is that if you access this line, if you want to read the value of this, if this transistor gets on, basically you're connecting these two lines together, and the charge from the capacitor is going to go through this bit line. So you're going to actually charge this to this bit line, and think about this bit line as another glass here. So basically the charge is going to move from here to here. All right. And as a result, the charge is actually going to go down after one read. Right. So that's why reads are typically destructive, because whatever you have is going to actually leave. And if it's empty, then nothing to leave. That's fine. But usually, if it's one, it's gonna, you know, flip to 0. So in order to fix this, we usually do what we call a memory refresh. That is, whenever we are reading something, we also refresh it and put it back. Okay. But the other problem that DRAM has is this unintentional leakage. Okay. Because what is really happening is that not just for the reads, but this capacitor is not a perfect capacitors. So over time, even if we don't read this cell, there is like a tiny bit of leakage from this, that, you know, the leakage, the charge actually leave. Okay, so you also have to occasionally refresh each line. Okay, so these together is creating this potential issue that, you know, if we don't refresh in correct time, then the charge is going to go down and down and down, and there will be a point that, for example, if you're storing 1, your data will be equal to 0. Typically, there's what we call a Vmin, or minimum amount of voltage, that if the capacitor voltage is below that, we consider that as 0. If it's above that, we consider it as 1. So what's really happening is that for each individual cell, we need to figure out a right time for refreshing each cell. If you miss that, then your data going to be, you know, the data going to be changed and corrupted. Okay, so this is like really what is happening. You're constantly refreshing every single cell in your DRAM in order to make sure that their charge is up. So every time that you refresh, your charge goes back to 100%, gradually goes down, then you refresh. It's the same story that we have with our cell phones, right? If you use your cell phone, your charge goes down, you have to refresh it, you have to charge it again to goes back. Okay, so that's a normal operation of a DRAM. That's what we expect for DRAMs to work like this. Okay, so that's fine. What is happening is this row hammer attack is essentially doing this, that if I open and close this row, which means I read this row, it will cause you know, more leakage on the other adjacent rows. Okay, so for example, if I open and close this row, so I was supposed to just read this row, and I can refresh it, so everything should have been fine. And these other rows also, are periodic refresh should fix all those issues. But what they have found was, if I read this frequently, like often, like, you know, many times, if I read this, there will be more leakage in this adjacent rows. Okay, and this is something that we didn't predict and we didn't expect to happen. All right, so as a result, what will happen is that you know, during the row hammer, you would expect that this thing's gonna go down like this, and then you, of course, you refresh it and go back up, and then goes down like this and goes back up. But with row hammer, if this is an adjacent row, what is happening is that each time that I'm actually accessing the adjacent row, there will be this extra amount of drop in the charge. And then by the time that I was supposed to, you know, refresh, this charge is already pretty low. And actually, when I'm going to refresh this, I'm not going to refresh it all the way back up. I'm going to read this and think that this is actually indeed 0. So I'm actually going to completely deplete it after the refresh. So it never actually goes back up to 1, because when I'm refreshing, the way that refresh happens is that you don't know what you have stored, right? So you're going to read the value If it's 1, you're going to refresh it to 1. If it's 0, you're going to refresh it to 0, right? So if it's here, it means that it seems to be 0 to me. So what I'm going to do is that I'm going to actually write 0 to it. So actually refresh kind of completely killed the data that you have stored here. All right. So the culprit really is this extra things here. So this extra jumps here is the reason that the row hammer is successful. So why this happens? So by the way, before actually talking about whys, this is the impact on this drop is not universal and it's not consistent for all cells. There are some cells that jumps higher and more. There are some other cells that's kind of like jump a little bit. So for example, this green one kind of survive of this row hammer. So although that you're kind of accessing the adjacent rows, this one just a little bit drops. So by the time that the refresh happens, it's still above the threshold. So when you actually refresh it, it goes back up and it survives, right? But this blue one and this black one does not. They go a little bit lower and they're gone. Okay, so it's not the same thing for all different cells. So each cell is a little bit different. And why do we have this in general? Why do we have row hammer vulnerability in general? The reason is that we are actually building these cells very, very close to each other because we are talking about very, very compact nodes, 3 nanometers, 5 nanometers, 7 nanometers. And there are actually, electromagnetics and electric fields effects when I'm actually accessing this cause, the field that creates by accessing this will actually, create some effect, some electric and magnetic effects onto the adjacent rows. And that's why there is a tiny bit of switching that is happening on the adjacent rows as well. So it's not the perfect switch that you just access this particular row. By accessing these rows, since these are very, very close to each other, there is actually higher orders, and higher impacts of electric and magnetics that cause the leakage into the adjacent row. That's really what happened. So if you actually look into DRAM and row hammer, you will see that older generation of DRAM was less vulnerable to this because they were actually physically they were more distance. There was more distance from each other in those versions. But as we move to a higher technology and more complex technology nodes, this actually the problem with row hammers actually becomes more prominent because they're just really, really close to each other. Think about it as some sort of a wall that you have between two rooms. If this wall is so thin, then of course any sort of noise gonna actually penetrate to the other side of the room, right? That is really happening. What's really happening with the way that we are building DRAMs. Okay. Any questions?
So I'm not an E person, but I'm curious. I know sometimes like you have one high, sometimes you have one low circuits. Does that matter in terms of brightness?
What do you mean by one high and one low?
Like sometimes high voltage is 1.
And
sometimes high voltage is 0.
Yeah.
Matter?
Doesn't matter, right? Because for example, if your high is 1 and low you're 0, then row hammer is basically flipping 1 to 0, right?
I guess I mean like as an attacker, do you need to know that about the system? Or is it?
So it depends on what you're trying to achieve. What you probably need to know, yes, but that's really easy to know, right? So you write your own data and you read it back and see what happens, right? So for example, that's an easy way to kind of knowing this. But generally the problem is not how you map your zeros and ones. You either map your 0 to 0 and 1 to 1 or the other way around. In either case, since your charge is going to go down, that data will be corrupted, whether it's 0 to 1 or 1 to 0, either one of those, right?
With an example like this, you can really only make a bit shift from 1 to 0, right? So does that really limit like what you can do with this, or is it?
So as in, like, for example, if you want to transit it the other way around?
Well, I'm just saying, like, if you were trying to purposely put in a certain set of
Numbers, yes.
right, you wouldn't be able do a whole lot with it unless you're just trying to like corrupt something.
Yeah, so I mean, what I'm showing here is more of like how the concept is working. There are actually attacks that kind of like take it a step further and show that, for example, okay, how do I use this for something real? But bottom line is that it can be useful for creating the fault, right? So it creates the fault as in it do the bit flips that you don't want to. The next question is, okay, how do I use this? You can use it for various different things. For example, you can, let's say that your data or your key has been stored on that particular line. Or let's say that your credit card or something like that has been stored there. If I flip that, then essentially I corrupt the integrity of that. So integrity is simple to do. If you want to do even more, such as information leakage in that, then there will be another layer of attack that needs to kind of combine with this. I don't have any particular example at the moment, but there are ways that you can combine this with other known attacks.
What if we refresh the other two rows at a lower frequency? So if I'm refreshing R3 at like 50 times, I refresh R2 and R1.
That's a good observation. So what they can do, there was one question. I'll get back to this after the question. Yeah, go ahead.
So, how does the attacker know which data is written, which data?
So how the attacker knows where is stored where? You probably want to kind of find the victim. Okay, so what you know is the things that you have access to, and the things that you don't have access to probably are good candidates for attack, right? So that's usually what the attacker does, that they know where the data is, and usually they know where the kernel has been stored. And typically the very first victim that they want to attack is the data within the kernel. Okay, so they kind of like, either guess where the kernel is stored, or even try to read the address first, or you may want to say that, okay, anything but me, I'm going to just flip. All right. So, and then eventually I'm going to get to what I want. All right. Again, in order to get the details of like how you can use this for useful purposes, I definitely recommend to also take a look at Rowhammer's attacks in real cases, because Rowhammer itself is just an observation, as in I can flip it. How can you use it for more serious attacks is a separate story that you definitely want to look at. Any other questions? All right, so going back to your suggestion. So the question was, okay, if I have this idea that, I'm gonna access this, and I know that the adjacent rows are kind of also, problematic. Why don't I also refresh these, right? If I refresh these lines, then regardless of how often I access this, these are also safe, right? If I go back here, essentially there will be a drop, and as long as this drop is not as big as this, I should be fine. And in reality, that's the case. Okay. So what will happen is that they actually found that this does not work, because the moment that you're refreshing this, you are now impacting the adjacent row to that. Okay. So they found that if I access this many times, this will create an avalanche kind of behavior, which this will be refreshed. And refreshing this is as if that I'm accessing this many times. So this is going to be impacted. So if I say, okay, now let's do 2. So let's refresh this and refresh this. Then there will be this one and this one actually going to be impacted. So in fact, there's actually, there's this very nice paper called Half Double Attack by Google recently. That's actually also making a lot of noise. That shows this, that even if you were refreshing, you were supposedly, fixing this issue, but also refreshing these two, I can intelligently, time this aggressor, and sometimes maybe, cause the refresh here, that if I time this perfectly, it's going to actually create flips on the far end, adjacent rows. And then if you add this to your refresh set as well, then I'm going to attack this one and this one. Okay, because generally, if you remember and if you pay attention, what is really happening is that accessing adjacent rows cause the leakage on the other one, regardless of whether this is a refresh or general access. So it doesn't matter if you refresh this one, the next one going to flip. If you refresh that one, the next one going to flip. So that's generally the problem that we're going to face to fix this issue. Question.
So what if we open there's like one of those, like the top or the bottom, and do it like switching around? So we refresh the target row and the row above it, and then the target row and row below it in the next iteration. So we can basically have the frequency of the row hammer fast.
It does, but again, it becomes an arm race between how fast the attacker accesses this and how fast you're refreshing, right? If the attacker accesses this line very often, then you have to also increase the rate at which you're refreshing this. And if they double their frequency, then you have to also double your frequency of refresh. So if you even, doing it half-half, the adversary will, increase their speed by a factor of 2, then you're going back to the same order that you were, right? So there's kind of like some limits that's going to hit at some. But there are solutions like this. So I'm not saying that this is completely irrelevant. There are ways that this might work in some cases. It's a good point. Yeah.
You turn on multiple rows at a time to like induce a greater electromagnetic field on the other ones, so yeah. It would make it easier, like if you were to do, for instance, on both sides of the row or two next to each other. Then
So what is the question? So you're saying the refreshing larger number of rows, or?
so if you were to switch two rows really fast, either on both sides of a row that you're trying to get a bit flip on, or just a block of memory and just turn it on and off really, really fast, you would have a greater magnetic field, right, over than just doing one row. So you would have a great.
Oh yeah, sure. As an attacker, you can also flip many rows together. Sure. Is that what you're saying? Like having a stronger attack?
Just saying it's kind of like this, but you just turn on all of the near aggressors.
Sure. At the same time, it depends. So the limitation for that is depends on how many rows do you have access to. So it may not be possible that you have access to both blue and green as an adversary, okay? Because these rows are kind of randomly placed in different places. Because usually, we put rows with page level kind of granularity, and that depends on how your virtual to physical address translation works. So you may or may not have it, but yeah, that's true. You may have multiple rows. You flip them all together, and then probably that creates even bigger issue. Sure. Any other questions? But yeah, so if you're curious how we actually fix this, there is also this nice paper recently that kind of does what we call a row swap. So the idea is that if there is this row that caused all the problems, why don't we actually kind of detect this or randomly just move the rows around? Because if this is the one that attacker is focusing on, what I can do is that after, let's say, 3 or 4 accesses, I will just completely take out this row and move it somewhere else and bring another row. And the adversary now needs to know which row has been replaced with what. And typically that's not an easy task for the adversary to do. Although this row swap one is also being attacked recently, and there was another one that's kind of fixed the row swap as well. So there's actually a nice kind of list of back and forth attacks for row hammer these past few years. If you're interested, just go and take a look at them to see what's kind of the state of the art in this domain. Okay, I think some of them actually do have their codes available, so that could be a good option for your projects if you're interested in row hammer or something similar to that. The defense, because these things you can actually run it in a simulator as well. Okay.
It's very expensive to refresh the whole memory in order to prevent any.
Yes, it's very expensive. So you definitely don't want to refresh. That's why one thing you can do is that you can refresh faster, right? So for example, if I refresh faster, I kind of fix this issue, right? But refreshing is really, really energy inefficient because you're talking about millions of lines, and you essentially read each line and rewrite each line. So lots of energy involved with this. So it's not efficient.
And what if, for example, the press every, let's say, 6 cells, so that this avalanche is basically counteracts when it meets the other one, so all of the cells are refreshed before it manages to go below the.
Maybe it's possible. There are games that you can play. Again, this is actually a very active area of research. So if you're curious, I'll definitely recommend reading some papers, see where they are, and maybe test some ideas. You never know. So maybe you can come up with a nice solution. So it's possible. Okay. Yeah. All right. So moving on, yeah, generally Rowhammer is very interesting, both observation, and there are nice things that you can work with it. So definitely, if you're interested as a grad student, you may want to, explore things a little bit further than what I just saying. So that's part of this, goal of this class. All right, so let's switch gear and let's talk about other things. The other one that is interesting in terms of faults is what we call jamming on contaminations. Okay, so as I told you before, jamming also considered kind of a fault, but it's a special type of fault. The goal of jamming is not creating some bit flips, but it's jam some inputs that was supposed to be read by the device. Okay, so creating some form of mask. The most common example of jamming is for RF systems, that you have an antenna on an RF device. You were supposed to get some message, right? And you were supposed to, translate this message and so on. So instead of actually I flip this message or I create some fault, what I can do is that I can generate another stronger RF signal, such that this original RF signal is buried inside this stronger signal that I'm creating. Okay. And as a result, what will happen is that the antenna will receive this stronger one, and it never knows what the signal that is buried under this stronger signal is. Okay. Although there are, anti-jamming techniques for sending and receiving. There are modulations that are robust against jamming and so on and so forth. But in simple, terms, there are ways that you can actually jam the signal that you are sending. So that's really important, especially for communication. For example, let's say it's a war. Soldiers wants to send each other's messages. The adversary, what they do, they don't want to change the messages, but they want to just shut down this communication between these two groups, right? So they jam all the signals. So essentially, you cannot really contact your other, fellow soldiers and teammates and so on and so forth, right? So that's an example of this. Contamination is a little bit more involved. So contamination means that you send some signals that later on you're going to gain advantage of. All right, so you're going to send some signals that are not real signals, but they look like real signals, or you send some messages or change some messages strategically, such that at later stage of the system, you use that in order to launch your actual attack to the system. I'm not going to go through the default, the description or detail of it, because it becomes very RFy. But if you're interested, definitely it's one of those areas that you may want to look more for jamming and contaminations. Okay, so let's also talk about countermeasures for faults. There are essentially 4 different things that you can do. You can improving robustness, which means that you improve your system such that it can tolerate more noise. You can do things like software control things in order to protect your system against the faults, right? For example, we talked about Rowhammer. We said that, maybe, okay, if you move the rows, then you are, fixing this issue, right? So that's an example of a software control solution. Of course, you can always detect faults, right? So similar to the way that we discussed for transduction attacks, what you may want to do is detecting faults instead of preventing them. And then finally, if you isolate your system, by isolation means that both physical isolation, as in you don't let the things to change, Or if you actually isolate it at the digital board, such that, for example, for something like Rowhammer, if you physically separate lines of your DRAM to pieces, different places, then something like Rowhammer cannot happen, right? Because you cannot like change things around you because there's nothing around you that you have to be worried about. Okay, so there are these ways that you can actually fix some of these issues. If you're interested to read more, there's actually some nice survey papers on fault attacks. There's one that is particularly targeting symmetric crypto systems because false is really, really popular in that domain. There's one about wireless systems. If you want to learn more about jamming and contaminations, probably read that. And then at the electrical level, there's also a very nice paper that's kind of servers different techniques for CPUs and FPGAs and GPUs and so on. This one is also talking about a little bit of Rowhammer as well. So if you're interested, go and take a look. To summarize the discussion on fault attacks, generally, combining this with transduction attacks and what we call sensor security problem, we are actually facing this problem even more these days because systems are vulnerable to various types of physical, analog, and digital attacks. And they are not even caused by bugs. They're mainly design oriented, right? So we haven't even started talking about the software issues that we have. These are just the issues that we have on the physical side of things. And we talked about transduction types of attacks that you change something in the environments and goes all the way through your system, or you can actually be more intelligent and actually create faults into your system. Okay, so that's where we are with the system. Your participation today is Meadow.
What is it?
Meadow, my cat. Okay. Any questions? All right. So keep in mind that, starting next week, we're going to have the paper presentations on Monday, right? Probably on Monday, I'm going to maybe start with the presentation and then do the rest of the lecture. As I said, presentation is going to be, if you're 4 people, 12 minutes. If you're 3, 10 minutes. And then your paper reviews are also due on Sunday night. Just pick one of the 3 papers and submit your reviews. Reviews are individual. Somebody asked me about that, whether you should do it in group as well. No, your reviews are just, each person has to do it alone. There was also a question about your final project. I'm going to talk about that next week, okay, because you're still having the first project. Any questions about the logistics before we move on? Is that clear? Good. All right. So now let's actually go one step further. All right. So we said that, okay, the sensors are not operating correctly. The hardware is not operating correctly, and that causes problems. But what if they actually do operate correctly? What if your sensors is actually reading what they're supposed to read? What if your hardware is doing what it's supposed to do? Are there other ways to attack this system? And interestingly, there are many, many more, right? And these are actually way more popular than what we discussed so far. So we said that, we said that we can have kind of like, static, behavior of the system. We can boot the system into some good known models and secure it. We said that then things start to, become dynamic, and that's where the problem starts. And the problem can start from the sensor side of view, but the problem can also be some other regular interaction with some other users, with the network, with maybe the actual, human user. There could be other problem as well. Okay. So what could happen in that case? There are actually software, vulnerabilities in this case, or in some cases, software hardware vulnerabilities that could also create potential attacks to the system. Okay. So we're going to also talk about these groups of attacks that has nothing to do with the sensor or the physical domain or the analog domain. It's just a pure, description and implementation of your software actually can cause these problems. You're probably well familiar with this, but essentially what is happening is that they eventually find some way to inject some malicious software into your memory, to your system. Okay. And then they manage to find another way that execute this malicious software. Okay. So you find a way to inject, and then you find another way to execute, and that's where you're going to actually do something malicious to your system. Okay. These are generally called, malware attacks. How actually this is happening, why an attacker can inject something and can execute something. Two main reasons. There are bugs in your system and in your design, or there could be human errors that cause the system to download something malicious, right? So all these phishing emails or this questionable links or files that we are using every day, they are actually reasons that many of our systems are infected with this attacks, right? And then essentially what they do is that the attacker designed their malicious file in order that once it penetrates your computer or your system, they can somehow find their way to be executed. So it's not just penetration, but it's also somehow getting executed. And malware is very, very sophisticated in doing both of them, right? So to find novel and smart ways of getting into your system, and then also finding an interesting ways to actually being executed. And unfortunately, the examples are plenty, and it's actually on the rise, similar to other problems that we have in the past. Okay. And then not only just malware and just downloading some file from the internet, there is also another class of malware that we usually call fileless malware, that you don't really need to download anything. It's just the way that they, exploits the vulnerabilities in your program in order to launch something and reuse some part of your program. You probably have heard about buffer overflow. You have heard about return-oriented programming. So these are examples of this type of attacks that has nothing to do with you downloading something. They're actually using and knowing that there are some intrinsic vulnerabilities in your program they use in order to attack. I'm going to talk about fileless one next week, but let me talk more about those that are kind of like malware types of attacks. So as I said, the fileless one typically corrupting your memory, injecting some sort of malicious code, or reusing some part of your own memory. That's really, really interesting because they don't even need to download anything to your computer. They're just going to reuse part of your programs that already exist on the computer to actually launch something. And we call it return-oriented or code reuse attacks, okay? So what are the objectives and how? Similar ideas that before, right? We want to attack integrity, we want to attack availability, and we want to attack confidentiality of the system. The how part I'm going to talk about next time in the next lecture. But generally, this is what we call the war in the memory, right? The memory corruption attacks that the attacker managed to inject something to your memory, run it, and then that's where you're going to be compromised. All right. So let me talk about malware first, and then I'm going to talk about fileless malware and buffer overflow and code reuse attacks. So what are these files are actually coming from? As I said, they're coming from of these wrong things that we typically do, right? So we click on different links, we install wrong files and folders to our system. If it did not do those things, typically your malware cannot penetrate your system. All right. So that's really, again, goes back to the fact that since we are doing interaction with the open, world and environment, we are making ourselves vulnerable to these kind of viruses and attacks. Okay. There are different types of malware. There are actually, lots of, different groups of malware. There are viruses, there are worms, there are Trojans, ransomwares, there are bots and botnets, there are adverse, spywares, rootkits, and as I said, there are flawless as well. And there's also what's called malvertising. By definition, malware is any piece of software that created with the intention of causing harm to your system. Okay, as I said, this harm could be integrity, it could be availability, it could be stealing something from you, it could be asking you for some ransom. Generally, anything that causes any harm to the computer system is called malware. All right, and there are a whole bunch of different types of malware that I'm gonna, in the next 10 minutes or so, hopefully, I'm gonna talk about different types. Anybody who has been, impacted by malware in their lives? What was it?
Oh, as a kid, I started playing with the family computer.
Uh-huh.
And go on sketchy websites.
Yeah.
So,
What did you download?
so I started playing Grand Theft Auto San Andreas.
Uh-huh.
I tried to mod it. And I ended up like getting virus every time. So
What was it? What happened to your computer when it got
you get
infected?
pop-ups at some point.
I
It
see.
just got like really slow, and then my
Okay.
dad would like take it to somebody.
What did you do? You just delete the entire thing and
They just wiped it.
I see.
Yeah, they fixed it.
Did you play GTA anymore or
Yes. I still play.
anybody else? Yeah.
My previous work, we uploaded WannaCry
Uh-huh.
and infected somebody. Well, no, sorry, that sounds really bad. It was more like a learning opportunity where we show people and then we decrypt it and fix it and show how to get rid of it.
Uh-huh.
Mostly like a learning experience, but just like playing around with WannaCry.
I see. So you were, as a company, you were showing that you have the capability of fixing WannaCry?
Yeah.
I see. So what was like some form of an antivirus or malware detection, the product?
We were essentially like dehashing it
Uh-huh.
and then it would just clear everything and make sure it's out of your system.
Sure. You had another one?
My little sister's school just the other week got hit by a ransomware attack and she had a 2-week spring vacation.
Oh, that's nice, right? Yeah, that's like when the presenter doesn't work and you have to go home, right? So that's kind of. So yeah, ransomware these days are the most popular types of attacks, malware, and it's awesome for this, governmental kind of public universities, hospitals, and so on, because they typically don't like follow specific guidelines, and they have data that they want, and they also want they cannot afford their system to kind of be down, so they're willing to pay. So that's really fertile environment for adversaries, unfortunately. Any final comments, stories about malware? Anything in the past, recently? Okay, so let me actually go through these one by one. So there are different kinds, and really what is making them different is the goals that they're trying to achieve, the ways that they're kind of penetrating themselves, and the way that they're kind of like spreading themselves. Okay, so typically the difference between the malwares are this. At the end of the day, as I said, all of them are caused to do or plan to do some harm to your system. So at the end of the day, they're all just malware. But some of them are doing something specific that the others don't. Some of them penetrate your systems in some ways that the other don't. And some of them propagate through your system than the other does. If I want to group them, generally there are two groups of malware. There are ones that are kind of created to designed to create damage, and there are some that are designed to just spread. Okay, and as a result, you typically, as a malware designer, you start with something that can spread, and then you kind of like add it with the damage. So it's kind of like a missile that has like a warhead, and then kind of like have a a piece that is just going to go. So the piece is going to take it to the place that it wants to explode, and then the warhead really explodes. So it's kind of like the malware is kind of following the same story. Virus is kind of like the most popular, most famous types of malware. The way the virus works is that it just attaches itself to some benign application. That's why the name virus. And that's the easiest way to kind of penetrate to your system, right? So you download some seemingly benign application, and it's actually, the application itself is okay, but there's just the software within that, there's part of the software that's kind of stitched to it that actually kind of like, then it's kind of gets detached from the actual software and then starts attacking. So typically at the beginning, it's dormant. Once it's reached to the host, this is actually when it's get activated and start attacking the system. The virus is also designed to spread themselves as much as they can, because generally for all these malware, the design is doing damage, but they're also doing widespread damage, right? So if you can actually attack one system, why not attacking multiple systems, right? Because then you can have more impact. And then one thing that they can do is that they can change, so that they can also launch another malware and another malware and another malware, so it actually can propagate all the way through. Have any of you heard about this I love you message cards that we had before in emails? That was a good example of viruses. You can click on this link and read more about it if you want to. This postcards that back in the day people sent to each other after Christmas and so on. That was kind of one of the examples. So other than viruses, there are other things. There are worms. Worms is actually this piece of software that is designed to kind of just spread itself. Okay, it's kind of worm through your system. And typically worms are designed to be independent of the host. So if the host is Windows versus Linux versus other operating systems, worms are designed to be agnostic to that. That's why they're really good at spreading themselves, because you never know where your worm's going to end up. So you want to design it as agnostic as possible. The worm itself could cause damage by depleting your resources. So one of the main ways of attacking a system is denial of service attacks, where you have many different worms in your system, and your computer becomes slow. Probably yours when you were downloading that thing from GTA was type of a worm. But typically worms are first step of something more widespread and more significant, okay? So you usually want to use worms, and then on top of that, you want to kind of like be able to download something else, and that thing will cause problems. So usually this WannaCry or this other ransomware attacks are usually starts with some form of a worm, okay? SQL Slammer was like one of the very famous ones, if you're interested to learn more. Trojans is another type of malware. The difference between Trojans and others is they're like Trojan horse, so they look benign and then suddenly they transform to something else. So if you actually try to kind of like look into some statistics of that software at the beginning, they may not look malicious, but at some point, under some conditions, they activate it, they get triggered, and they attack. Software Trojans is less important than hardware Trojans that later on we're going to talk about. So hardware Trojan is also another type of a hardware malware in some sense. Trojans typically don't spread themselves because they actually designed to look benign. So they're just benign looking of themselves is actually the way that they can spread. As I said, the counterpart of the software Trojans is hardware Trojans that later in the course I'm going to talk about. Okay. There is ransomware that, as I said, is the most popular type of malware these days. And the most famous example is actually the WannaCry that happens and make lots of news in 2017. The way ransomware works is it actually has this payload that goes through your memory and essentially encrypt everything that you have in your memory. Okay, so it has a method to spread itself, gets into the computer. Once it's actually reached to your system, all it does is just using something like an AES or an RSA to encrypt everything that you have in your computer. Okay, so by encryption, what will happen is that then your boot sequence won't work, your operating system won't work, because essentially, if everything in your computer is encrypted, then your computer doesn't work, right? So typically, what happens is they encrypt everything and then just leave one program unencrypted, and that program is some form of a log or message that whenever you boot your computer, that's going to be showed up, and usually say that your computer has been, encrypted. If you want to use it, send me this amount of money, usually in form of Bitcoin. Then I'm going to send you the key, and then you can decrypt it, right? So that's the interesting thing about ransomware is that it's not destructive in the sense that you can actually recover your data if you want. All you need to know is the key, right? If I as an attacker give you the key, then you can decrypt it, and everything goes back to normal. So that's why ransomware is kind of like this popular type of attacks for the adversary, because there is a really simple way to earn some money for the attackers. As I said, typically the last part of a sophisticated attack is ransomware. You usually use some form of a virus or a worm to penetrate and spread, and then you want to then download the payload, which is the last piece of the attack, which could be, for example, WannaCry or something like that. Again, if you're interested, definitely go and read some articles about WannaCry. It's really sophisticated attacks, very widespread. Actually, attack many different things as a result of this. Okay. Let me pause here. There are maybe 2-3 more that I'm going to talk about at the beginning of next presentation. There's bots and botnets and malware and so on that we're going to talk about next time. Okay.